Hello, welcome back to the channel where we develop software for self-driving cars. And we make it available to everyone with a computer because we use Carla driving simulator. Here we break the daunting task of autonomous driving into smaller manageable blocks, so you could get into it at your own speed. And you can have some fun by staging things in the simulator like this little trick. Today we're going to be doing a code walkthrough, detailed walkthrough of all Python code that relates to this video that you see in front of you right now. And many of you have asked me to just do more detailed session on what's involved, and here we are. Let's get into it. I have created a new subfolder in my self-drive GitHub repository, and it's called RL full tutorial. When you expand it, there are a couple of main files that you see here. The first one, which is what you see open now, is the train file, which is what you need to kick off when you need to start training things. So essentially this is the engine, how long you want to train it for, how many iterations you want to do it, and those things, and we'll walk through it now. And then the second most important part here is the environment.py file. This is where all the environment things and logic and what happens every single step, how rewards are given, all of those things. So the second one, we go back to the first main file. When you kick it off, I put here that you need to make sure that simulator is running because it needs to interact with the simulator. And I also put some terminology here just in case some of you get confused. I found myself being confused about the episodes and time steps at the beginning, but it makes a lot more sense now. So the episodes, one episode is one game. A car starts and then it keeps going until it crashes or there is a time limit. So I think you find that we'll jump to our environment in a second. We run in up to 15 seconds. So if the car hasn't smashed into anything, if 15 seconds are over, a new episode will start. So when an episode starts, there's a car that is being spawned at a new location or random location. And then when episode ends, that car has crashed or the time ran out. So that makes sense. The individual time step is just one iteration within the simulation. So the car gets the image from the camera. It makes a decision based on its current policy what to do, and it sends that decision into the simulator. And of course, as part of this time step, it also gets back information about what the reward, the cumulative reward that it received in this episode. So it's trying to adjust its policy given that how many rewards it gets. Okay, so that's one time step, just one single frame. The camera image goes to the car makes a decision. It also gets rewards back from the simulation or from the engine, rather, from the RL engine, and it passes on controls to the simulator, like to, for example, turn the steering wheel to 20 degrees or something like that. So there's obviously a lot of time steps per second that is going on, but it doesn't really matter like how quickly it happens. All you need to know is just one frame with one cycle of the simulation. Okay, with that out of the way, if we just walk through very quickly key sections of the code in the train module, so we just have all of our imports. By the way, whatever you need to install in your Python environment, it's all here. Whatever you can see from the import section, that's what we need to install to make sure we can run this. And so some of the things that happen here. So this model directory situation is around where we want our policy to be saved. Because according to this, all of my models go into self-drive models. So because I've defined it, so every time I train something, there is a new folder being created. And so if, for example, I was just trying to get this working, just double checking things, you see a lot of these folders are empty. They only will get populated if at least one iteration of training has finished, okay? So at the end of each iteration, we get a new model saved. And unfortunately, my luck is not with me today. I'm not having any of these things populated. Okay, so this is an example where there were 2 iterations part of that training, and this second one is a later file. And if we go back to our terminology, iterations is essentially how you organized here, like these things. How many iterations do you want to run as part of your training session? So if you run 4 iterations, there will be 4 stages of training. At every single end of that stage, a new file will be saved on your hard disk, which is that policy at that point in time. Okay, so it kind of allows you to have audit trail of what you've been learning so far as part of this session. You can also technically, this is not part of this tutorial, but then you can open the latest policy and continue training it while changing some of the parameters of the environment. But today is not the objective. Today we're just trying to get off the ground, to get training started. So that doesn't really matter. And you can also try to do a few things differently. Like on 500,000 iterations takes about few hours, depending on how long the duration of your episode and what your computer is like, and many other factors. So you can actually have less time steps but more iterations. So you can play with these parameters to allow you to have more snapshots of your model as it being trained. So you can potentially, if you want to, you can go back to some different ones and test them differently and how they perform. Okay. So this is where we need to save our model. And then I've also got some code that I'm not using it, but it could theoretically enable you connect TensorBoard, so you can view the training process as it goes, all the stats. However, when you run this, there is a periodical, like every few episodes, there is a window, a snapshot pops up in your command prompt where you can see what the average reward is at that point. And you don't need a TensorBoard running to see if your model is performing better, because you can see your average reward statistic going up or not going up or going down. So you can kind of get the idea of what your model is doing as part of just, running this script itself and nothing else. I've also got a couple of things like what's happening, like for example, before I create an instance of my environment, I just doing a print connection to environment. So in case something failed, you can kind of see to what point the code has got to. And the next point I've got here is after I've done the initial reset of the environment, I'm also sending a message, hey, first reset is done. Then I create a new instance of the PPO RL sort of policy algorithm. And the most important thing, like this is done in iterations. So if I have 4 iterations here, what I'm doing essentially is running this learn command here. And then at the end, when it's finished, it saves. And essentially this is how we get our snapshots of different models saved as we go. So if you want, you could theoretically save a model every 1,000 steps. You just need to put 1,000 instead here, but also you need to increase this number. Obviously there should be a lot of iterations to compensate, because you can't just train a model in 5 minutes. It needs to go through a lot of examples, and that's how you do it. So hopefully this code makes sense. It's quite simple, and you can Google and copy different examples of this from multiple sources and from Stable Baselines 3 itself. And the other important point, that the actual module Stable Baselines is only used in this piece of code. Like the environment itself does not need it, because it's all concerned around how it interacts with the simulator. But the training itself happens here. That's why we're using Stable Baselines 3 here. And essentially it's being used when we declare an instance of this model, and then we start training it here by running model.learn, and then we save it. Okay. And that's probably it around the train module. Now we're gonna jump back to the environment, which is where we define everything. Now you can see that I've collapsed everything at the bottom here. All of these additional methods that I define here is they all collapse, so we go through them one by one. But from a top level view, the kind of things that we need to know here, all of the imports that we need, they here. All of the modules that you need to be installed in your Python environment, they mentioned here. So if you don't see something here, it doesn't necessarily mean it has to be installed in your Python environment, but all the necessary things are here. And then we're going through a section of constants. The first one, as I mentioned before, what is the limit for your episode to run? That's 15 seconds. Later, I've actually been trying to experiment with in synchronous mode, where I don't need to see what's happening in the simulator. I just want iteration loops of learning to be as soon as possible. So you probably need to change it to number of time steps as opposed to number of seconds, because if you define it as seconds and you track in time, by definition, regardless how fast your computer is, you're waiting for 15 seconds, up to 15 seconds for each episode. So in the future, you might need to change it, but for now, we just keep it in seconds. Then the things that go into our image, and you remember our image is actually slightly bigger. I think it's 480 by 640, all the images that we cut, throughout my tutorials, but for just to speed things up, I scaled them down to 240 by 320. Okay, so it's essentially I think 4 times less, because each height and width are divided by 2. The spin constant is to train a model to force it to see lane markings and edges of the road. We can't just let it run straight, because it will just cheat and run straight all the time. You need to force it to see lane markings, and that's why we need to give it a random angle of spin when we start a car. And the 10 here is 10 degrees, so it's left or right 10 degrees, random from up to -10 to ±10 will be applied to the car at a spawn point of the car. And then these constants are essentially how we also need to crop image. So we take the bottom 50% of the image, because that's where the road is, and then we take 90% of the width of the road, because we don't want fringes to the very left and to the very right. So you can play with these things. You can just completely ignore and put width as 1, so in which case everything will be taken, but it's there just in case. This thing, you can ignore it, because it probably works for synchronous mode for future, so it doesn't really matter for the way we use it now, but I somehow left it in here, so I might just try to delete it, and I need to test how it works, so this thing doesn't really matter. Now, this is a very important thing, where initially you need to set this thing to true, which means show me the preview as training happens, because as you tweaking this to work, to making sure you can work and use it, you need to test what's happening. You need to see what the car is doing. So if you set show preview to true, so a couple of things will happen. You will have the top-down view to the car in the simulator, and secondly, you've got the little semantic camera popping up periodically, so you can see from the car, from the view from the car's camera, what's going on in front of it. All right, and then we go into defining the actual environment. And by the way, how this all came about and how I was trying to work with it is there is a great tutorial by Sendex that you can see how he starts using stable baselines 3. But essentially, if you follow this gym library sort of convention, you start a new environment from a gym normal template, and then you just tweak it. And then there is also tutorials how you can use there is a code that's stable baselines 3 that allow you to test your environment if it fits if it will work with stable baselines 3, but this one definitely does. So all you need to know that in the very roots of these environments there is this gym library convention, and they've been followed. There's probably some other attributes of these objects created according to this gym library as we do it, and I'm just following the convention that there needs to be a few things, there needs to be a reset, there needs to be a step, method, and there needs to be, like anyway in Python object-oriented programming, there needs to be init method here. So, and I'm also defining few constants that live within the environment object. So, for example, like show preview is essentially just a copy, or show cam refers to show cam here. Right there, it's just passes it onto the object on the environment, the instance of the environment. And there are a few constants that essentially the height and width is the camera, steer amount, don't recall what this means. My apologies for that. And then the camera position, this all make sure that where we view the road from is kind of as close to possible to where Tesla Model 3 camera is mounted on the car. So in theory, you get the very similar image from the sort of dimensions of what the road should look like from the view of the car. And these constants of how far up from the center 1.3 of the car the camera is mounted, and how far forward it's mounted 1.4, and it kind of gives you the mounting point of the car that mimics the Tesla situation, or Model 3 Teslas, I should say. Preferred speed is it's just that, like, because I'm using maintain speed method here, which is just trying to get the car going at 30 km an hour without actually reinforcement learning, trying to learn accelerator. So this model just does steering, right? To get you off the ground, I'm just showing you step by step what it takes to learn the car how to steer, to train the car how to steer. And that's why we control the speed just programmatically, okay? So, and what it means that we could go very quickly. So depending on what our speed is, and our preferred speed is 30 km an hour. So if we exceeded preferred speed, then we accelerator input is 0. If we are within the threshold, which is like 2 km an hour of the top speed, we go in at 0.7. And then if we are within the threshold, or we are between 28 and 30 in this case, we only use 0.3 kilometers an hour. So this is very arbitrary, it's very simple, it's just to get the car moving at a constant speed, okay? Because training how to use the throttle of the car is not part of this exercise of us training the model, okay? So all we're trying to get the car do is to learn how to steer roughly and not to crash into anything. All right, so this is all of our constants, and now we go into the init method. So, and this I just copied from examples on Stable Baselines 3. So very first thing we need to do is to define our action space. So as I mentioned to you in my other videos, I'm actually switching to reserving action space for throttle and brakes at the same time, in which case it will be something like this. Like, for example, we also have 9 possible options for throttle and maybe 3 or 4 for braking. Like, for example, full brakes, some brakes, no brakes, something like that. But for now, because the objective of this is just to tell you and get you how to make the car learn how to steer, we're just focusing on the steering only, okay? And what this 9 means is the model can try up to 9 possible steering wheel angles altogether, okay? So to give it sort of less number of options to choose in between, to get it quicker to learn what you wanted to do. Obviously, it will have its limitation. Imagine not being able to put a steering wheel in a very specific spot and only being able to put it in one of the 9. Obviously, one of them will be center, and then it will be, you know, a bit to the left, a bit to the right, and then more to the left, more to the right. So effectively, all in all, 9 options, including all the way to the right and all the way to the left. You'll see later how it's mapped to the actual steering output to the simulator that we're trying to get out of it. But for now, just remember we only have 9 options. And then this here is just how we calculate cropping factor from the image. So, and then what we do here is, because we're using pre-trained model that you, by the way, have in this folder, it will just refer to it directly. You don't need to train it. I've got train code here for you to have if you want to train another model. It will show you an example, but then to train a new model, you need to generate your own images, and you need to, that will take some time. Then you need to make sure that the model trains and it actually gets to some meaningful results and improvement, and rather than just random steering. So therefore I just gave it to you here straight away so it could be used. And remember, again, the objective of the model is to squash the overall image with, all the, what do we have here? We've got 240 by 320, and then we crop from it to a lot smaller representation, which is, 7 by 18 by 8. And that allows the model to navigate through and see. It's kind of very filtered vision of what's in the image, but if you give it to a human being, they wouldn't make any sense of it. It's just, smaller, more condensed representation of what the car sees in front of it. Okay, so we've calculated all the cropping dimensions here, which is essentially just a simple formulas how to apply all of this sort of. You need the bottom part of the image 0.5, and you need the center 90% of the pixels in that bottom part. So that's what's happening here. Then we do connections to the simulator, because remember, this is an init method which will run at the very start when you kick off the environment, when you create the environment. So the environment obviously needs to connect to the simulator, which is what's happening here. And then it will need to get the world object of the environment itself. And then it will try to get settings from the environment. And this is one of the things where, whether you want to see preview or not, will be passed on. So if you don't want to see preview, the environment will go, or the simulator will go into no rendering mode, in which case it's all becoming just black. You don't see what's happening in the simulator itself, but this will just speed up your processing. But initially, you just need to make sure this is set to true. So not only you see the little pop-up windows of the front-facing camera, but also you can see top-down view of the car in the simulator and what it's doing at the time. This is just to get you confident that you're running this code correctly and nothing is going wrong, and it will be learning. And if you sort of let this run for maybe a couple of days, you can then see the improvement of how the car driving visually. Okay, so it may be a good investment of time. Just let it run to see where you get to. Although, on the other hand, you can put this to false, and hopefully the training session will go a bit faster, and then you can just load saved model and test it with a different, slightly different version of this code that will just apply a trained model, and you can see what the car is doing in the simulator. All right. The next thing, so we applying this rendering or no rendering mode to the simulator. And then we go, okay, we're trying to get Tesla Model 3, and then here, which is where we load our image pre-processing CNN model, like it's right there. And then we run some code to essentially compile it, or to make it available to do the, not prediction, but conversion from the raw camera footage to this condensed representation of shapes 7 by 8 by 18 that actually goes into reinforcement learning engine. And also, if you show preview, you get a spectator. So, and the spectator object of the simulator is what allows you to move the spectator and kind of top-down view into the simulation and see the car top-down physically. Okay. So that was our init method. The next one that is, let's actually go through one by one. The cleanup is just what happens at the end of each simulation. We need to make sure we destroy all actors and destroy all cameras. So if there is a sensor or collision sensor or camera, which is also a sensor, so all of them need to be destroyed from each simulation, because if you don't do this and you run the next episode, the simulator will be clogged up with cars that are crashed or sitting in the center of the road. So we don't want that. We want to clean it up. And you'll see that this method being applied in, I think, reset or in the step method. Maintain speed, you've seen already. It's just depending on current speed. You pass the speed, which is S, into this method, and it just gives you, if you're within 30 kilometers an hour, just ease up on gas. That's what it says. And if you exceed 30 k's an hour, the gas is 0. So that's quite simple. Then we have apply CNN little function, and all it's doing essentially is if you needed to apply a safe convolutional neural network, you need to make sure that you meet certain conditions or criteria. Like, for example, the image should be in the float 32 format, and then you normalize it, and then you add another dimension which is required just because to apply this predict function, which is essentially right here. You've got the CNN model, you take the image and you apply the model to the image in a predictive non-training way, and then essentially on the output you get the result. But then that extra dimension that you created here to be able to run this mode, this statement, is you need to remove it again. So it's kind of there is a problem solving every time you try to make predictions with neural nets, and it's just putting all of this tweaking into one method. Hopefully it makes sense to you. And here we come to one of our main methods or things that we do. It's not a function because it's object oriented, so it's like a function slash method. So what happens every single step? Step is what happens in time steps. Remember, we've got definition of time step. Time step is a fundamental reinforcement learning terminology thing, right? So, and what we do here is what happens each time we loop through simulation. What needs to happen here is we need to understand where the car is. Okay, so we get in transform of the car, which gives us the location and orientation of the car, or location and rotation elements of it. So if one thing we would like to do with that transform is, if we've got spectator, if we show preview, we need to move the spectator to just about where the car is. And what we do here is we essentially do Z delta, like we're raising spectator 20 meters above looking down. And looking down is what you do here. Pitch minus 90 is 90 degrees down, which is when the camera drops down looking down, okay? And your minus 180, like you don't need to have it, it's just arbitrary, because in one particular town it was more convenient to see this way. But don't be surprised that your car in some cases will go up, down, left or right, because it's not really automatically orientated exactly how the car is, okay? But it definitely follows the car. You can see what's going on. And the way it follows the car is the location is taken from this car transform or vehicle transform here. So we're only doing delta to the rotation of the car, which is actually we're going up 20 meters, which is location, and then we change the orientation of the camera to look down, which is this, okay? Then we also need to set up our step counter, because in the init method we've got, I think somewhere we set step counter to 0, or it could be in reset. It's confusing things. You have a init method like everywhere, but you also have reset method, like what happens every time the car dies and you need to start a new one. So there is another set of logic here. But for now, let's assume that this the counter is restarted in the reset method that you will look into a bit later. So this is what's happening. We take our steering, like imagine we get one of our 9 steering predictions, okay? So what we do to apply steering to the car is if the reinforcement learning came up with one of the 9, so it could be 1, 2, 3, 4, 5, or 0 to 8. And this is our mapping where we say the middle 4, because we've got 9 from 0 to 8. The 4 is kind of the middle point, and that's where we say 0.0. And that's our straight position. And then we do just by 5% going left to right from it, then 1% going more left to right to it, and then 0.5 to the left, 0.5 to the right, and then all the way extreme positions 0.9. So we don't go to -1 and +1, we're just limiting it to something more. I don't think we need to go to turn that hard to the full lock, okay? And to have only 9 options, it just gives the model, again, less thing to predict between, so it just makes it easier. That's what we want. We just at the very beginning of reinforcement learning, we just need to make sure that you guys all get off the ground and can do this, so it doesn't really matter if we are precise and all that. I'm sure you can do it later yourselves, hopefully. The other thing we want to do is, as we train, we kind of periodically want to print what sort of steering angles the model is coming up with. So after we mapped our actions from 0 to 8 to exact steering angle, you want to output it into like the console, the command line. And we only do it every 50 steps. So if the car dies before 50 steps, you don't see anything. But, you know, if the car ticks over 50 time steps in one episode, you can see some things, what the car is trying to do. And the reason it's done is, imagine, like in earlier stages of this, I was seeing the car cheating and doing full circles in just, you know, full lock to the left and do circles, because that's how you can make a lot of distance technically, but you're not getting anywhere. So because I needed to punish for it all, you need to know what's going on. So if all of a sudden you see these little pop-up messages that the steering angle is -0.9, -0.9, -0.9, that's an indication for you that the car is in a full left lock and it's just going around to the left and the left and left and left, okay? So that's why we have this periodical output to give you a flavor of what the car is predicting at the moment or training to do. This is where we get the speed from the simulator, from the car, what the current speed of the car is, and the conversion of that velocity thing, because it gives you essentially a speed in 3 different dimensions. So Pythagoras theory, you just do this, and I think because it does meters per second or something like that, that is 3.6. That essentially allows you to convert to kilometers an hour. And estimated throttle, remember we had this function up there, maintain speed, that we just calculate from current speed that we are, what throttle input into the car we need to apply. And this is where everything hits the fan. So we predicted our steering, we calculated what throttle we need to have, and we're not braking here. So we sending that command to the simulator. Okay, car, our throttle is that value, our steer is from the action space. And you see, the actual fact of you referring to the action space that you defined in the init method, it means that's where you kind of tell the reinforcement learning engine that's what you need to predict. So it comes to you from the RL engine. Okay, so each time step you get this new action as a result of running this reinforcement learning. Okay, so you might be asking, okay, how do we calculate what steering angle, or how do we tell RL engine to calculate steering angle for us? But essentially that's just us referring to the action space, and that's where everything happens automatically for you. And that's one of the advantages of using off-the-shelf kind of reinforcement learning environment without having to create one yourself. Trust me, you can just get lost there for quite a while, unless you want to specialize in it, in which case be my guest, of course. Now, the other thing next thing we calculate the distance that we travel from our initial location. So we know how much distance we made in total, and that's another thing that prevents us from going in circles, because even if you go in circles, you're not going to actually get far from that initial starting point where the car initiated. And then this thing is the other thing where if you show preview, our front camera object is you using CV2 just imp show and using 1 is like in milliseconds. It will give you a very quick version of that video, because it will be showing you this image every time step, and it will look to you as a video, because the wait key here is, I think, 1 millisecond. So it's not 1 second, it's 1 millisecond. So that's why it will still happen quite fast. And from this section on, we actually begin the most interesting part of reinforcement learning, which is how your reward logic is everything. So you, first of all, we need to punish for lock duration. So I've got the kind of code where it tracks how long it's been if the car steering has been beyond 0.6 degrees left or right. And it sort of tracks that time. And then later, if you can use it here, so it calculated this lock duration, which is time difference or time duration. And if anything greater than 3 seconds, you subtract 150 points. You effectively slap the car on the wrist and say, hey, no, don't do this, okay? And then, but before that, this is how you start the reward calculation. You set it to 0, and then you're done is effectively the simulation finished or not is also false, like the situation continues. And then you because you've set up your sensor in, and you'll see it in the reset method. If any event is added to your collision history, you essentially means you crashed. So, and the way we detect collision in the reward calculation, we just see if there is any objects in this collision history list. And if it's greater than 0, we're saying, okay, the simulation finished, we are done, and then we subtract 300 points. And this is where we use that cleanup function. So if we finish in an episode, we just clean after ourselves, okay? The same happens here. If the lock duration event occurred, we also setting done true and stopping that episode, so it will go into the next episode automatically. And then if lock duration is not 3 seconds but longer than 1, we subtract 20 points. So you see, we're just trying to be kind of nimble and flexible with our reward policy. It's not like a very harsh threshold and then something bad happens and then nothing bad happens up until that point. So we don't want to have that situation, so we kind of make it smoother. So as soon as we get more than 1 second duration of lock, we just start giving negative rewards straight away. And then you see the old code that I used to do, like how you could reward for acceleration, like if you needed to, but we don't need it for this tutorial, so it's commented out. The other thing we do is, remember our episode is kind of, you can align it with your episode duration. So because we've got like 15, 25 something seconds, we need to say, hey, if you travel less than 30 meters, we do a little reduction of the rewards. It's like we punish you for not going far. But if you start going beyond 50 meters or up to 50, beyond 30 up to 50, then you start rewarding the car. And then the best thing happens if the car gets outside of 50-meter radius from the initial point, and that's when you start giving slightly more rewards. And that's what essentially pushes the car to go and make more distance. Because if we look at the main things that we've got to prevent us from doing bad things, is we punish the car for crashing, which is a big reduction of 300 points straight away. Then we reward the car for making distance, especially making distance beyond 50 meters. And that's essentially your main levers to make the car do the right things, okay? And then we've got some household activities such as episode start and tracking or checking how long it's been in the episode. So we actually locked episode start time, and now we comparing if we add 15 seconds what the current time is. If it's within 15 seconds, the episode will continue, otherwise it will fire off. We're done, we clean up, and we go into the next episode. And then at the very end of this step, what happens is the image from the front camera will be, well, a couple of things. This is where we crop it at the very end. So we get the image from front camera, which is because we've set it up later in the reset section, because it's automatic. So what we need to do is we need to apply crop to it, and then we need to apply our model to it. So at the end, you get this nice condensed array that you pass on to the outcome of the step. You also give the reward and whether the episode is finished or not. and that concludes each time step. That's what goes out from each time step. You've got new image, pre-processed image, you've got reward from this time step, and whether you finished or not. Okay, so that was time step or step method describing time step or what happens. Now we're going into another important method that is standard requirement for stable baselines 3, reset. So what we've got here is we've got collision history to 0. There is no collisions, there is no lane invasions, and there is no actors yet. And then we're trying to get random location on the map to start the car. By the way, you may have noticed that in our step method, we're not actually using this in lane invasion history, which is my mission here. So it could be your homework to make sure that in the reward policy in this step, you not only check for, where is it? Yep. It will be very similar code to this. So in you check if that object of lane invasion history, if this thing will start having at least one element, it means you invaded someone else's lane. And I think what it means is like it's more like oncoming traffic as opposed to just, you know, in the same direction, but not 100% at this point. Okay, so we established the place to start a car, then this essentially starts a car. We maintain actor list and we add the car or vehicle to it. Then we set the initial location to, because the car has started, we effectively lock initial location for future reference to calculate distance from it, okay? And then there is a normal code that you can find in my very initial sort of step 1-2 tutorial on Carla, how to start sensors and cameras. And this one is pretty simple. So we also have a couple of like process image supplementary things, which is where we essentially just getting rid of another alpha channel, the standard color pixel comes, you know, RGB is only 3, but this one will come as 4. So we're just essentially getting rid of that extra part of the pixel which represents alpha channel, which we don't need. And I found it initially from everything that I was researching about Carla, even from Carla themselves. So that's a standard way of operating, of converting it to normal RGB image with just 3 elements of each pixel. And if we go back, that's where it's used. When we set up the sensor, we essentially run this listen command, and that listen command is what makes the sensor live in the simulator. All right, so, and then remember we just started the car, we just need to apply control and give it a couple of seconds. And the reason we do that is because we're trying to give this car just an initial spin at the beginning. What I found, without the delay of 2 seconds after starting the car and applying control, sometimes it's just not enough time and you end up having the car being completely straight or not quite the angle that you wanted. So all of this is just to make sure that you can apply this, calculate this random spin angle and then apply it to the car. And then you initiate your collision sensor by running the listen and initiate your lane inversion sensor, which we've just seen that we're not actually using, but this is how you do it. And then we wait for the front camera object, which is our semantic camera sensor, wait until it's initiated, and that's when we start our episode start clock. We set the steering lock as false. We set the steering lock start time is none. This is like it's not on yet. So we're just declaring some of these variables that will be used as part of our object or self referred, which is what self referred to. We've got step counter. We set it to 0, and then we also apply 0 brakes, 0 throttle to the car. And then we run the first image and send it to the output. So we essentially doing the very same thing that we've done at the end of the step method, because the reset will need to give the first output or the first camera image that the car sees upon initiating itself. Okay. And then there is also a couple of supplementary collision and lane detection things being used, and this is just to be able to use your collision sensor listen, because that's the convention that Carla wants you to follow. Like, you need to have these methods defined what's happening. Like, in what it means is every time something happens from the collision sensor, you just get this event added to the list. That's what's happening, okay? And that is all structure of our environment. Okay, let's try this. So what we do is we come to train, and we just do run Python file here in VS Code. And remember, we set show preview to true. So, okay, this is exactly what we're seeing, right? So you can see the simulator view of the car down, and you see the little pop-up window with the semantic camera. By the way, for this demo at the end, I did fix the lane invasion sensor as well. So it will now detect, you saw the it crossing the line and immediately causing collision. So yep, I fixed it as I was doing this video. So hopefully you enjoyed it. Please hit me as usual with questions. If I can, I will answer them. Thank you very much for watching. Good luck with making your own. Thank you. Bye.